Okay, so we're going to begin with a couple of announcements here. Just make sure that we're all on the same page. And, oh, that's not the right slide. All right, here we are here. So announcements. First of all, if you haven't already made arrangements to get a copy of the textbook, please do that as soon as possible. It's a valuable resource to get a second opinion on how to explain this material. And I'm going to do my best to explain it in a clear way, but sometimes you need to hear things from a different perspective than I'll provide it. The homework assignments mostly are going to be questions that I myself have written, and so you're not going to need the textbook, maybe with a few exceptions. You won't need the textbook for the homework problems, but you will need it to learn and understand. So that's the first bullet point. The other is, of course, I am accepting calls on Microsoft Teams just so that both of us can get a feel to how to do this. You need to call me for these 10 bonus points before Tuesday at 5 p.m. Tuesday, September 1st at 5 p.m. And you're welcome to try calling me outside of my office hours. It's just that I may be in another meeting or away from my desk, and so it's during the office hours that you have a much better chance to get a hold of me. And I'll pick up unless I'm already in another chat with a different student. Homework 1 is going to be due on Thursday, the 3rd of September. Before 11 a.m. So our class meeting is at 11 a.m. and you have to submit the homework assignment before class that day. And so let me show you where you can go to get homework number 1. If you go to our class page in Blackboard and click on the homework tab, then you can see homework 1 is there. And if you click on the PDF file, then it'll bring that up and you can see the homework problems here. So there's 9 of them for this assignment. And so it's due on Thursday, a week from today. Some of these problems you can probably solve even before today's class. Other problems you'll solve after today's class, but there are going to be a handful of things that we don't cover until Tuesday. So if you start going through this and you kind of realize, I don't know how to do problem 9 yet, well, don't panic right away. We're going to cover some other stuff on Tuesday of next week. So you'll still have 48 hours to solve those other problems before the assignment is due. All right, so that's all of these announcements. Today what we're going to do is cover viscosity and the gas laws, and we'll do that after briefly looking over the syllabus, which I've also posted onto Blackboard. And so you can find the syllabus just down here under the course schedule. So if you click on the syllabus, let's go over some of these policies, and it's always important to know, for instance, how the course is going to be graded. So this has the contact details for me, and so you can call me on the phone or stop by my office or get in touch by email. And of course there's also Microsoft Teams, which is probably the best way because then we can see each other and I can share my screen if I want to bring up some example, or if you want to share your screen so you can show me what you've been working on. Teams is the best. Here's my office hours. I mentioned it during our lecture on Tuesday, but it's Monday, Thursday, and Friday during the times that are indicated there. And I'm welcome to talk to you at other times if you just want to give me a call, or we can schedule an appointment if I'm available. There's a big variety of university policies that at some point in your academic career you should go through all of them so that you understand what the rules are that govern your student experience at Marshall, and the academic calendar is identified with a link as well. The course description is that we cover fluid properties, hydrostatic forces, stability of floating bodies, equations of fluid acceleration and motion, dynamic similitude, internal flow, and computer solutions. So this is a 3-credit-hour undergraduate course, and the rule of thumb I always heard when I was going to school is that for every credit hour you need to plan on 2 hours for outside study and solving homework problems. You know, so if you're a full-time student and you're carrying, for example, 15 credit hours, then that means you would be in class 15 hours a week and you need to set aside 30 hours a week for studying and homework. So that means between the class attendance and the other studying and homework, then that would give you a total of 45. And so, you know, that's roughly a a full working week if you're a full-time student. So here's the ISBN for our textbook, if that helps you to track it down. Then there's a list of objectives and outcomes, and I don't want to read those to you. I know you can read, so I'll leave you to go through the outcomes and objectives. We will be covering each one of them in great detail during the classes themselves, but I do want to briefly go over the details related to the grading basis. So we're going to have 2 midterm exams and a final exam, and so there's 3 exams total, and each one of those exams is worth 25% of your course grade, and then the other 25% comes from homework assignments. Now, in an ordinary semester where we were face-to-face, I'd also give you a couple of quizzes, and the quizzes are typically 5 or 6% of the homework grade, but it's not feasible for us to do those quizzes this semester. It would take away from too much of the instructional time, and so I've just put the points for the quizzes back into the homework assignments, and so I've increased the value that you get from the homework assignments. The schedule of topics mirrors what you've already seen if you've looked over the schedule that I posted and reviewed in Tuesday's class, and so this will not be any different from the course schedule document that we previously reviewed. But what I do want to spend a little bit of time talking about is my expectations having to do with academic integrity. And I covered this during the lab, but not all of you were taking the lab. So I want to emphasize that when you turn in your homework assignment, it needs to be your work and what you did exclusively. The homework assignment you turn in shouldn't be something that your friend helped you to solve. It shouldn't be a solution that you got from another student in a previous semester or a solution of a problem you found online. It needs to be your work. And when I identify cases of academic dishonesty, then those are going to be punished pretty dramatically. So on the subject of homework assignments, I dropped the 2 lowest homework assignment scores from your calculation of the overall course average. So that means that if you accidentally forget to submit an assignment before the due date or the time that it's closes, then you can use one of your 2 dropped scores on that. Or if you do all the assignments, then I'll just drop the lowest of your homework scores. But because I feel like that's pretty generous, dropping the 2 lowest homework assignment scores, I don't accept any late work. It's simply not practical for students to turn in homework late when we've got as big a class as we do and when the homework grader is going to be going through your assignments as soon as you submit them. We want to be able to provide timely feedback, and so that means we can't just leave it open-ended for when homework assignments get turned in. So there's a due date and no exceptions unless it's an official university excused absence. So are there any questions about that policy so far? I see somebody's microphone, I think, is unmuted right now. That's why I wondered if maybe there was a question. So please don't ask for an exception to the policy. You don't send me an email saying you missed the deadline and is it okay if you turn it in late. I'll just be a little bit disappointed if you do that because the policy is very clear. You either turn it in on time or you don't turn it in, and there's no in between. So some more details about the expectations with academic integrity is that copying homework from either an online solution, from another student, or any other source, it's not allowed. So don't copy the calculations, don't copy the pattern of the solution. It's not okay to look at some other solution and figure out how to solve the problem and then you put the numbers into the calculator, because operating the calculator isn't the important part in solving engineering problems. The important part is the problem solving and the conceptual setup. And so it's not okay to just mimic what somebody else did to solve the problem. It is okay to talk about the homework problem with another student, to discuss the concepts in general. And when you've solved your work and somebody else has solved theirs, it's okay to check your answers and see if they match up. And if they don't match up, it's okay to help people to find their mistakes. But there's also some unacceptable behaviors. It's not okay to show someone every step-by-step they should follow to solve the problem, because if you show them all the steps, then now they've been robbed of the opportunity to learn and struggle and get stronger. And that's what it takes, is it takes a real mental engagement to figure this stuff out and to retain it well enough that you're successful on the exams. So you won't be ready for the exams if you don't solve the homework yourself. For the similar reasons, I discourage students from group working problems simultaneously. And what I mean by that is, if 3 people are sitting at a table and solving homework together, what really happens is that whoever works more quickly is going to end up just having their work mimicked by the other people. And so work individually, and then you can check answers if you like. So are there any questions related to academic integrity? The incoming homework assignments are going to be screened for inappropriate collaboration, and people who engage in academic dishonesty are going to receive a punishment that's more severe than a 0 on the instrument in question. So let's say there's 9 problems on a homework assignment. Even if you only copied 1 out of the 9, I'm going to give you a -1 or worse on the assignment, meaning you don't even get a 0. You get less than a 0 if you engage in copying on the assignment. So just to avoid the risk of that, please don't submit work that isn't yours. Okay, well, that's all I want to talk about with the syllabus. It's available online, so I'd ask you to read over it in full and let me know if you have questions, but we're going to move on to covering some of the content unless there are any questions now. All right. Well, if there are none, then let's talk about viscosity. First, I wanted to point out that next semester I'm going to be throwing this slide into my presentation. You may remember that we had a discussion about whether at the bottom of the ocean water compresses itself because of the weight of the water above the bottom of the ocean. And I thought that was a really interesting thought question. And so, you know, I learn from your great questions sometimes. I learn, you know, what's interesting to students and how can I be more thought-provoking. And so I'm going to throw this slide in next semester, and I just wanted to illustrate that, you know, even though we're talking remotely right now, it still is possible for us to have a good interactive experience. And so I appreciate the questions when you've got them. It makes it more easy from my perspective to teach. Okay, now this is a photograph, and does anybody want to guess what this is a picture of? Is this water?
Looks like honey to me.
It looks like what?
Honey.
Honey. Good. That's right. And what are the clues that that's honey?
There are bubbles trapped inside it as it's flowing.
Good. Very good. And so seeing those bubbles, what does that imply? Like if this was water, we wouldn't see those bubbles. So what does it mean when you have the bubbles?
They can't readily escape.
They can't readily escape. Good. And so there's something about this fluid that makes it so that the air bubbles can't escape. Another interesting thing is if you look at the taper, can you see my cursor? It's never clear to me whether students can see my mouse cursor. I guess you probably
Yeah, I can see it.
Okay, good. That's must be a new feature for Blackboard Collaborate Ultra, because in the spring students couldn't see my mouse cursor, but you can now. So another clue that this is not water, besides the color, obviously. Another clue is if you look at the taper there, it's kind of, if this was water, it would be going into individual droplets. You know, the water accelerates fast enough, it speeds away from the spoon as you pour it out of the spoon, that it wouldn't be cohesive and pouring out into a sheet like this appears to be. All right, so there's something about this fluid that's a little bit different from water. Let's watch a video clip that also addresses this same issue. All right, so I have, here we go. Bring it into full screen mode here. I'm going to mute it, and All right, so fluid on the left, fluid on the right. Something's different. The person is shaking these two different fluids. They're both clear. There's the same amount. They're in the same kind of container, but when you shake the one on the left, it sloshes around easily. The one on the right doesn't slosh around. So when you're shaking the container, you're applying a force to the fluid. When you apply the force to the fluid on the left, the fluid responds to that force. And so it's deforming. The force that's applied is causing the fluid to deform relatively easily, it seems like. But the fluid on the right isn't deforming as much. You're applying a force, but it's not sloshing around. Okay, now let's see what happens if you pour it. The fluid on the left, which is water, pours easily. The fluid on the right, which is glycerin, it pours really slowly. That's thicker than honey. It's thicker than syrup. Just looks so delicious, I want to put it on a stack of pancakes. Glycerin and pancakes, it's a winning combination. So this illustrates the principle of viscosity. So let's talk about viscosity in detail. Now, to understand viscosity, we have to define some terms here. You may remember from previous courses that you've probably heard the word strain. And so strain is the deformation of a physical body under the action of applied forces. So we just saw in the picture forces being applied and the fluid deformed. But solids also can deform when you apply a stress. I wonder if I have my ruler in here. I do. Brilliant. All right. So I've got this metal ruler. I don't know if you can see the picture of me. It's probably pretty small down there at in the bottom of your screen, but I'm holding up a metal ruler, and if I press on that metal ruler, I'm applying a force right now, and it's deforming. Can everybody see it's formed into an arch? Now it's not moving anymore, it's stationary, but I am still applying a force. So right now, the physical body is deforming, and the strain is that deformation under the action of the applied force. So a solid has this proportionality factor between the shear stress applied and the shear strain. So the stress is the force, the strain is the deformation. And the relationship between the two is defined by shear modulus. So this is steel. How do you think it would be different if this was titanium? Maybe we don't know a lot about titanium, but maybe you do. What do you know about titanium compared to steel?
It's more brittle, it would probably break.
It's more brittle. It would resist the deformation. If I applied this much of a force, I think it probably would, but well, if it deformed this much, it probably would break. But just think about my weak little fingers, my weak engineer fingers. I couldn't break a titanium with these little weak fingers, but what would happen is it just wouldn't deform as much if this was titanium. So steel, it deforms a lot. Titanium, it deforms a little bit. So there's this material property, the relationship between the stress that's applied and the strain that is experienced by that solid. The proportionality factor is the shear modulus. Well, there's a similar thing in fluids. In a liquid, that proportionality factor is called viscosity. And the difference between, one of the many differences between a liquid and a solid is that in the case of a liquid, it continues to deform as long as the shear stress is applied. So an example of that is if you put a propeller into a tank of water. The water is going to continue to deform as long as the force is being applied. Whereas in the case of a solid, it only deforms, it stops deforming even though you're still applying a force. And if I want it to deform more, I have to apply a greater force. But a liquid will continue to deform. And so it stays in motion as long as the stress is applied. So The reason why I compared the solid and the liquids is just so that you kind of understand that there's an analogy here. The analogy between stress and strain in the solid and stress and strain in liquid. We're going to look at some figures. I hope that will make this a little bit more clear. Gavin asks, is there still a yield stress when dealing with liquids? No, there isn't. All right, so one of the principles that one of the applications of viscosity is the fact that a river has a different velocity at the top as it does at the bottom. So we have a river here in Huntington, the Ohio River, and you maybe have noticed that when you look at the top of the water can be, it looks like it's moving pretty quickly. But if we went down to the bottom where the water is in contact with the soil, the velocity would actually be 0. So when we talk about the velocity of the river, there's not just one velocity. There's a whole distribution of velocities. There's a spectrum. And here is a velocity distribution. And what it shows is that if we are down here at the bottom of a stream, the velocity is 0. But as you go higher up and further away from the bottom of the stream, the velocity is increasing. And so up at the top of the water, the velocity is higher. And so this slope, dy dv, is just how quickly the velocity is changing with an increase in depth. So let's watch a video clip that introduces this idea that at the bottom of flow, where the water is in contact with a stationary solid, the liquid velocity is 0. Let me bring up another little YouTube video here. Oh, actually, I think that this video isn't on YouTube. I think it's one that's on my hard drive, so I'll just bring it up that way. All right, dragging it over to the screen now. All right, now this is a little bit murky. It's maybe hard to see what's going on, so I'm going to explain it before I play the video. I'm going to give you a sense of what we're actually looking at. This is a straw. So there's a straw that's going down into a flume. And most of you went into the fluid mechanics lab this week, and in the back of the room there was that big long channel. You can think of it as like a big plastic, it's like a plastic simulation of a river. So there's clear acrylic on either side, and then the bottom of it is plastic. And so you're putting water down this channel, and it's similar, I guess, to a rain gutter. Think about the rain gutters on your house. It's just a long rectangular channel that carries water. So in this case, what's happening is that water is flowing from the right to the left. No, I don't remember what direction the water is actually flowing. We'll see. So this is a straw, and it's going to be injecting a dye. And we're going to see what happens to the dye that's being injected. Okay, so they're going to put the straw down at the bottom, and right now that straw is touching the bottom of the channel. So think about it's a simulated river, and this straw full of dye, they inject a little bit of the dye. So can you see the green tracer? So they're injecting some of that green tracer, and so it's like a big blob of dye, and it's not sticky. It's a water-soluble dye, so it's not like it's glue or anything like that. But it will stay at the bottom because the velocity down there is essentially 0. Now when you take the straw back up into the rest of the stream, you can see that these ripples and turbulence kind of indicates that the water is flowing from the right to the left. And so the dye is acting as a tracer. But there's still this big clump of dye down at the bottom because the velocity of the liquid is 0. But when they put a spoon down in there and stir it around, the dye goes away because you finally put enough velocity to make it go downstream. So that's just an illustration of the no-slip condition. So the question is, can it be assumed that the farther away the liquid particle is from the stationary surface, the faster it goes? Yes. That's a great question, and yes, that's the correct observation. And this velocity distribution is kind of an illustration of that effect. The farther away you get from the bottom, where you have the no slip condition, no slip boundary, that just means that the bottom of the river isn't moving. The bottom of the river is stationary, and the farther away you get from the bottom, the faster the liquid is, because that solid surface down there is applying a resistance to the movement of the fluid. All right, so if we define some of the terms
Would
here,
this not be experienced on the sides as well?
yes, it would be experienced on the sides. So that was like a clear plastic acrylic on either side, and you're right, it's not just the bottom, it's any place that the water is in contact with, it's going to have that no slip boundary. Okay, so we can think of, okay, another question from Zach. Aren't the velocity / location of the fluid particles dependent on the location of the force applied to the fluid body? Not sure if I understand that question. Yeah, I'm sorry, Zach. I don't understand that question.
I mean, like if you have a propeller down near the riverbed, it's going to be moving the fluid particles in the river faster towards the bottom. So I just wanted to make sure that that's not a general rule that we apply, that it's always true that the farther away from the stationary surface the fluid particles are, the faster they'll be moving.
Yeah, okay, I understand your point. Yeah, you're right. Because, for example, the spoon, when the spoon went down to the bottom and he was swishing the spoon back and forth, well, then that's no longer true, that that's the lowest velocity. So there are, like if you have external interventions like a propeller or the spoon, then you can defy this general velocity distribution trend. Okay, so viscosity is the resistance to flow. Remember when you had that glycerin in the beaker and it was being shaked back and forth and it was resisting flow? Flow is the response to the forces that are applied, and viscosity is resistance to that deformation. So in this figure, V is velocity, Y is the distance from the bottom, which is the no slip condition, and then mu is viscosity. And sometimes we call it absolute viscosity, sometimes we call it dynamic viscosity. Those two things mean the same. Absolute viscosity, dynamic viscosity, those are two different names for the same exact thing. And sometimes we just call it viscosity. So any three of those terms are interchangeable. And it has units of Newton seconds per meter squared. The shear stress is the force that's applied per unit area. And so if you think about the units of shear stress, it's going to be force per area. And so shear stress, the relationship between shear stress, the deformation, and viscosity is this equation that's shown on the screen here. So remember what I said earlier is that viscosity is the proportionality factor between the shear stress that's applied and then the response of the fluid. So shear stress is force per area, and then dV dy is the rate of strain. dV dy is basically how quickly the velocity is increasing the further away you get from the boundary. So think about this velocity distribution. Right now, let's say this figure is a river of water. What if it was a river of pancake syrup? Well, that would be delicious. But what we know about pancake syrup is that it has a higher viscosity than water does. And so there wouldn't be as steep a curve if this was pancake syrup. You'd have to go further away and maybe the velocity would just be a little bit higher. So it wouldn't be deforming as readily if it had a high viscosity. So you can think of it that way. Another illustration example is just thinking about the fluids that you walk through. It's easy to walk through air, but if you're in the swimming pool and you're trying to walk, it's not as easy. You can't walk 4 miles an hour through a swimming pool because the fluid is getting out of your way not as readily as air gets out of the way. When you walk through air, it deforms out of the way really easily. Now, if you're driving a car at 100 miles an hour, there's some serious wind resistance there. The fluid is deforming and it's applying a resistance force, but it doesn't require a very big velocity to have some resistance force through a more viscous fluid like water. So water has a higher viscosity than a gas like air. So why is it easier to walk through air? Because it has a lower viscosity. So there's less friction. You can think of it as resistance or drag force because of the viscosity of the fluid. Another way to think about it is that it's deforming at a higher rate than water can because the viscosity is lower. So back to this formula, if you have a low viscosity, then you can have a large dV dy for a certain amount of shear stress that's applied. So for, you're applying a shear force to a fluid, a low viscosity will give you a big dV dy. Then if it's a big viscosity, so if mu is large because it's pancake syrup, then for the same force, the rate of strain has to be lower. Air moves out of the quick rate when you apply a shear stress. Water and other liquids that have a greater viscosity will move out of the way more slowly. So here's that equation again. Shear stress is viscosity multiplied by dV dy, which is the rate of deformation or rate of strain. So if we graph it, you can see the difference between air, water, and oil in this figure. And what it's showing is, think about this vertical axis, which says shear stress. Remember, the units of shear stress is force per area. So a certain amount of force applied to a unit area is only going to get you a little bit of deformation for oil. So here's the curve for the oil. And so for a certain amount of shear stress, the oil is just going to deform a little bit. So think about shaking it side to side in the beaker. Sloshing it around, you're not going to get as much of a response with a viscous fluid like oil compared to water. Water's going to slosh around really easily. But for a certain amount of shear stress, what would deform the most is air. And so in the horizontal axis here, rate of deformation, you can just think of this as the response to the shear stress that's applied. And so the slope of the line, you can see here that we're calling the shear stress is A, and the rate of deformation is B. And so shear stress divided by the rate of deformation is how we define viscosity. All right. So viscosity is the slope of the line if we were thinking about it in graphical terms, which means it's the ratio of the shear stress to the rate of deformation. And when we were just kind of doing some general definition terms earlier, I suggested that one way to think about viscosity is its resistance to flow, because something with a high viscosity will have a high resistance to flow. A low viscosity will have a low resistance to flow. Let's look at another video. All right. So this is an experiment where we have several different fluids here. I think it's water and maybe an oil, honey. So what they're going to do to illustrate that there's differences in the viscosity is they're going to drop a ball into each one of them. And how quickly the ball settles to the bottom of the liquid is a reflection of how easily the liquid is deforming out of the way. And so, wait for it. It'll be worth it. starting on the left, the water, dropping that marble, oh, I think that must have been air because it looked like it fell really quickly. So air is a liquid, a fluid, right? Okay, this looks like an oil, and we could, with a stopwatch, time how long it takes for that ball to settle down to the bottom of the fluid. And so there's different viscosities and different speeds that it settles. And this one must be really thick because it is deforming out of the way so slowly. So these are just another illustrations of viscosity. And so you could characterize viscosity by how quickly the fluid deforms out of the way. Remember, terminology-wise, what we've been talking about so far is absolute viscosity, which is the same thing as dynamic viscosity, and sometimes we just call that viscosity. I'm going to introduce another term now, and that is kinematic viscosity. And kinematic viscosity corrects for the fact that some fluids are more viscous when they have a greater density. So there's kind of a co-varying relationship between density and viscosity. So a lot of equations that we use in fluid mechanics will have both the viscosity term and also a density term. And for that reason, and also to be able to express viscosity independent of a fluid's density, we sometimes use kinematic viscosity as a variable. And it's the ratio of viscosity to fluid density. So here's the formula for it. The formula is we take mu and divide it by rho. And so remember, viscosity has units of Newton seconds per meter squared. And density from our previous discussion has units of kilograms per cubic meter. And so if we cancel those terms out, remember a kilogram is a base unit, but a Newton is a kilogram meter per second squared. So if we were going to expand the units of the Newton out to its full base units and then simplify, what we get is that kinematic viscosity has a unit of meter squared per second. So it's length squared per time. So it's just another way of expressing a similar thing. So here's the terminology. Absolute viscosity, dynamic viscosity, and viscosity all mean the same thing, and we assign them the same variable mu. But kinematic viscosity is something different. It's where we're dividing that by the density. Now, shear force is when you multiply shear stress over an area that it's being applied. And so if we want to find out how to calculate the shear force for a fluid that has a certain viscosity and is experiencing a certain rate of strain, so du dy here means the same thing as dv dy. You probably already know from physics and statics and all that sort of thing that sometimes we use u for the velocity variable, sometimes we use v, but here what we mean is the rate of deformation, du dy. So the way that we use this equation, it's applied, and it's, of course, units of force is newtons. The way that we apply this formula is that sometimes there's a linear relationship between the change of velocity and the distance between two surfaces. And so rather than assuming a curved velocity profile, we just use a linear distribution of velocity with distance to simplify and solve some problems. So here's like a physical instance that we can use viscosity to do some calculations. Let's say that we have glycerin in a tank. Remember from one of the earlier videos, glycerin was the thing that poured out of the beaker really slowly. So what we know about glycerin is it has a large viscosity. It resists deformation when a shear force is applied. So what we have is this sheet of metal. It's a metal plate that's 3 meters by 2 meters. And so what that means is it has a surface area on the top of 6 square meters and also a surface area on the bottom of 6 square meters. So it has in total a surface area of 12 square meters. 6 on the top, 6 on the bottom. Now if we tow it through the glycerin, we have to apply a certain shear force. A force in order to get it to move through the liquid. Now what we're saying is we want to achieve 0.58 meters per second. We want this metal plate to drag through the fluid at 0.58 meters per second. And we're also given some technical data, like the glycerin's viscosity is 0.15 newton seconds per meter squared. And then also we know the distance, that it looks like it's closer to the top of the tank than it is to the bottom of the tank. So what the example says is it's 1.2 meters from the metal plate up to the top of this tank, and then 2.4 meters down to the bottom. So what we want to know is solve for F. How big of a force is required in order to achieve this total velocity of 0.58 meters per second? So you can see I've given you a hint. Is we're going to be using this formula. F is viscosity times area times du dy. And here I've said we can just use velocity divided by distance as du dy. But we've got two distances. We've got the distance to the top and the distance to the bottom. And so the total force is going to be the sum of the force on the top and the force on the bottom. So what I'm going to do is pause for a moment, give you a chance to get your calculator, piece of scratch paper, or you can solve this in the notes if you've printed those out. But I'm going to pause and I'm going to ask you to calculate F. Calculate the total force required in order to us to get a velocity of the plate moving through the stationary liquid if the plate's moving at 0.58. All right, so I'm going to stop talking. If you want to type a guess there into the chat box once you think you've got the numbers, I'd invite you to do that. That would be great. Back. We're trying to figure out the total force, and let me drag this solution over to this screen. Okay, so what we're given, we have the equation that defines force applied, viscosity, area, and rate of strain. We know the distance to the top is 1.2, the distance to the bottom is 2.4, the velocity, the viscosity, so those are all of our knowns. So if we want to calculate the force that's on the top of the plate, because the top is closer, it's closer to that location where the tank is stationary. So there's going to be a greater shear force there because the distance is less than the bottom. So you can see where I've substituted in the numbers, and the top force is 0.435 newtons, the bottom force 0.2175 because the distance is greater down to the bottom of the tank. And then the combined force when we add those two together is 0.6525. So any questions about that? All right. Well, great. That is a taste of what you're going to need to know in order to solve the homework. So, question?
Yeah, can you go over how we calculated the area that we needed to calculate this for? Because I know you said we need to do the top and the bottom, and we're doing 3 meters by 2 meters, so we have 6. But
Right.
I don't, like, why are we not just doing the face, like the surface area of the face that's dragging through the water?
Good question.
Or glycerin for that matter.
So this is the thin plate. You know, the thickness of this plate is so small relative to its top and bottom area that there is going to be a drag force having to do with like the front face of that plate, but it's going to be negligible compared to the drag force that arises due to the area on the top. So let's say, for instance, if this plate is a centimeter thick, so that's a pretty substantial metal plate if it's a centimeter thick, but still the area of that, if it's 1 centimeter by, let's say, 2 meters deep, that's going to have a really small area in contact with the fluid compared to 6 meters of area on the top and then another 6 meters of area on the bottom. So we kind of neglect the thickness of the plate and the interface, the like vertically oriented interface, because what's going to be by far the dominant surface area is the top and the bottom. And so we use 6 as A because we've calculated the forces on the top and the bottom separately because they have different distances, because the dy is different for each of those. So hopefully that addresses your question. All right. Are there any other questions?
So what about if the plate had like a bit of convexity to it? Would we use the same type of formula?
Well, I guess, if it's really convex, then now the drag force, like the projected area from the front would be different. And so, depending on how convex it is, we may no longer be able to neglect that the profile drag that we did in this example. So I guess it would just depend on how deformed it is. Let me give you another illustration, and this is of a homework problem that, okay, I got a question from Harrison here. Does the formula only apply to surfaces parallel to movement? Could it be used for the front/sides of a thick-sided plate? I'd say, yeah, it does only apply to forces that are parallel to the movement. And I think that you'll get a sense for how it applies as we look at a couple more examples. Let me bring up the homework assignment here. So in one of these problems, in problem 6, you have a cylinder that's falling down through a different cylinder that has a hole in the middle of it. And so there's oil that's inside that boundary. And so that lubricating oil is, if you think about the distance, it says here it's 0.003 inches thick. So if this inner cylinder is falling downward, then you're going to be able to have the velocity defined for you, 0.5 feet per second. And so thinking about this formula that we've just looked at, that would be the du, the given velocity, and then the, oh, wrong way. Okay, here it is. And then the gap distance of 0.003 inches would be the dy. And so here's the dv, here's the dy, and then the area. So the question is about what area to use. It's going to be the area that is in contact with the fluid. And so it's not going to be like, if we think about a cylinder, I'm holding up a water bottle right now, the applicable area isn't this bottom area of the cylinder, it's the side area of the cylinder. And so in this homework problem that you're going to have, it's the area, the outside area of a cylinder is, you first of all find the circumference. So that's circumference pi d, and then the distance. So circumference times the distance would give you the outside area that's in contact with the fluid. So that will be the applicable surface in that homework problem. And that homework problem is similar to a problem that I used to give out of the textbook. In that textbook problem, which this other one is similar to, there was a a cylinder that was falling down through a pipe. And so it was a similar thing where there was a gap distance. And so it's the gap distance between the two is what defines the dy. The dv is how quickly it's falling. And then the area will be the area that's in contact with the fluid, but not the top or the bottom area. It's the outside surface area where, you know, where's the gap the smallest is going to be what governs, because of in the formula, the dy being small means that you have a much greater force. Viscosity is independent of a fluid's pressure. And so the viscosity of a fluid doesn't change if it is being compressed and pressurized. Terry asks, by nature, will the cylinders always be concentric? I'm afraid I don't know what you mean by that, Terry. So here we have a cylinder. What is it you're asking? Do you have a microphone, Terry?
Yeah. So what I'm asking is, if you have that cylinder sliding down the pipe, like by nature, like would it be the path of least resistance for the cylinder to stay exactly in the middle of the pipe on its way down?
Gotcha. Yeah, that's a great question. And I think you said it exactly right when you said the path of least resistance. And so that cylinder wants to travel at the highest velocity it can. Not that it has like conscious preferences, but it wouldn't go up against the side wall, because then it would be falling more slowly. And so just in the same way that water flows through the path of least resistance, the cylinder would fall through the path of least resistance, which is going to be to maximize the distance around the edge there. So yes, it would. It would fall down the center of it. And it may like bang back and forth, but in general, it's going to maximize its velocity. Okay, so fluids don't change their viscosity based on the pressure that they're experiencing. And this viscosity arises out of the molecular forces within a fluid. And so fluids that have high cohesive bonds, molecular bonds inside of the fluid, are going to have those cohesive forces decrease as the temperature goes up. So viscosity does vary as a function of temperature. And you probably have seen that before when you change the oil on a car. If you've ever had the pleasure of sliding under a car and changing the oil, what you know is that if the oil is warm, it pours out really quickly. But on a cold winter day, if you don't let your engine warm up before you empty the oil, then it can drip out of there for hours. It just drips really slowly because it doesn't have the same viscosity. So the temperature dependency of viscosity is that in a liquid, the viscosity decreases as the temperature goes up. But ironically, in gases, the opposite is true. That when a gas temperature goes up, because the molecules are bouncing around more, since the molecules have more kinetic energy, that ends up having a slight effect that increases the viscosity of the fluid. And before we get into the Sutherland's equation, let me just show you the figure of that relationship. So this is showing the kinematic viscosity of two different fluids. It's showing that in oil, the viscosity is decreasing as it gets warmer. So down here on the horizontal axis is temperature. So with the oil, it's pretty dramatic. When you're down near freezing, the viscosity is high, but as the oil heats, the viscosity is much lower. So if you look at the magnitude of these units, it looks like about 1/10 the viscosity by heating the oil from freezing up to 100 degrees Celsius. With air, that slope isn't quite as steep. It does experience an increase in viscosity, but the effect isn't as dramatic as it was with oil. But I remember like when I was growing up, there was this airplane that they wanted to do a continuous flight around the world. I think it was called Voyager. It had a, maybe you've seen it if you've been to the Air and Space Museum. I think they have it hanging up in Washington, D.C. It has a propeller on the front, a propeller in the back. And what I remember about that is that they did it during the winter time because they wanted the air to be cool and have more viscosity, because if the air has more viscosity, then they're able to generate greater thrust with those propellers. And so the reason why they didn't do their attempt in the summer is that in the summer the air would be warmer and therefore would have they wouldn't get quite the same thrust that they'd get in the other case. So what Sutherland's equation does is it allows you to estimate the effect of temperature changes on changes in viscosity. So it's an equation that's empirical in nature, and it just allows you to estimate if you know the viscosity of a fluid at a certain temperature. So in this example, for instance, let's say that we know the viscosity of air at 50 degrees Celsius is 1.95 times 10 to the minus fifth Newton seconds per meter squared. What if we wanted to find out that same fluid at 95 Celsius instead? Well, what we have to do is use units of Kelvin in order to solve this. And so we're going to convert both of these temperatures from Celsius to Kelvin and then solve for the mu, the velocity at the new temperature, where we start off with the viscosity at a given temperature. So this is another one of those where I'd like to pause for just a moment and give you a chance to try out Sutherland's equation, because there's a homework problem where you do this. Let's try and find out what's the viscosity of air at 95 degrees Celsius. So that's going to be the unknown viscosity at a T of 95. And of course, you have to convert it from 95 Celsius to Kelvin. And the original viscosity of 1.95 times 10 to the minus fifth was at a T naught of 50 degrees Celsius, again, converting over to Kelvin. All right, so I'll stop talking, give you a chance to exercise your calculators, and I'll be giving out gold stars in the chat box to people who get it right. On the screen, just in case you're stalled, so that we can see where things are going with this. All right, so the first thing we have to do in this problem is convert the given temperatures into Kelvin, which is par for the course when we're dealing with gas type problems. And so our givens is that the initial temperature for which we know the viscosity, 323.16 Kelvin. The temperature where we want to know the viscosity, 368.16 Kelvin. And then we're also given the initial viscosity and the Sutherland's constant. And then you can see the substitutions that I made in there. Now, this is the first, but certainly not the last time, I'm going to point out a habit that I think is really important for engineers. And I think it's an important habit for you to be really explicit when you're making substitutions. And so in this example, what I did was I wrote the equation first, and then I showed the direct substitution for every component of that equation, including the units. It's really worthwhile to write the units when you're substituting things in, because for one thing, it'll help you to avoid mistakes of maybe substituting the wrong variable in the wrong place. You know, for example, if you write the temperature in Celsius accidentally, and so you had, you know, like 50 Celsius, and then this Sutherland's constant is Kelvin, then you'd see, oh, these are different units. I can't add it together. But if you just wrote the numbers, if you just wrote the number 50 and then the number 111, then you're not going to have that same like opportunity to recognize that the two shouldn't be combined. So in other words, what I'm saying is include the units when you write down the numbers, and you're going to make fewer mistakes. Also, it's just more professional and more neat if you include the units. And so the other thing I'll point out is that I don't try and do all the calculations in a single step. I kind of take a few steps, and so you'll notice that what I did here is I had the ratio of the temperatures, and then I write that number there before I do to the 1.5 power. And the advantage of having it in multiple steps is, again, you avoid mistakes, and you can check your work more easily. I think it's really a good habit on exams, for example, to check your calculations 2 or 3 times before you submit the work. You just want to make sure you didn't make a calculation error. And so if you do kind of like these intermediate steps, it helps to check your work. So in the end, you can see what we end up with is 2.15 times 10 to the minus 5th Newton seconds per meter squared. Any questions on these calculations? So you have, this allows you to estimate the viscosity of a gas when you don't have it like in a table. It's just a way to extrapolate. All right, so we already looked over these figures for the viscosity of air and oil, and this is a kinematic. So if you'll remember that the units for kinematic are length squared per time. There are some other ways to classify fluids. A Newtonian fluid versus non-Newtonian fluid. And what we mean by that, a Newtonian fluid is where there's a linear relationship between shear stress and shear strain. So water is a Newtonian fluid. The slope of the line is dynamic viscosity in a Newtonian fluid. But there are certain fluids that are a little bit funny. Maybe let me just show you the video clip before we go through the definitions in too much more detail. Let me first of all, let me see if I can copy that link and put it into my other browser. All right. Look at these kids walking on a fluid. Have you seen something like this before? Sometimes this is called oobleck, but really what it is it's just cornstarch dissolved in water. And so if they walk fast enough, they can avoid falling down into the fluid. But if they stop for a second, then they get stuck in the fluid. They go down into it. So this is a non-Newtonian fluid where the viscosity of it responds to the shear stress that's being applied. So let's look at this other video as well before we talk about it a little bit more. So copy link, and then I'll paste that over here. I'd love to have a swimming pool full of that non-Newtonian fluid. Oh, those golden fries. You didn't think you'd have to sit through commercials during fluid mechanics class, right? Okay. All right, so this is a high-speed camera, and that same thing, it's the cornstarch water mixture, and they've added some food coloring to it in order to make it more visually appealing. When you apply a force to it, then instantaneously the viscosity of the fluid changes. Like if you're not applying a force, it has a low viscosity, but as soon as you start applying a force, then the viscosity is higher. So it has a greater resistance when you apply a shear force. So look at the interesting patterns that arise because of the movement of that subwoofer. And then they get it going with the high-speed camera. Kind of interesting shapes. Hopefully they'll show us the high-speed footage here in a second. All right, here we go. It almost looks like an animation, right? But it's not. This is the actual footage. It looks fake. But what's happening is that as the subwoofer is moving, it's applying a shear stress to that liquid, And so the liquid's viscosity is changing as the force is applied to the liquid. In the lab next week, we're going to deal with this cornstarch water mixture so that you can get kind of a tactile experience of what does it mean when a fluid is non-Newtonian. So those are a couple of video clips. Now let's go back to these definitions. A non-Newtonian fluid could be a shear thinning fluid. And so in a shear thinning fluid, what happens is when you apply a shear stress, then the viscosity decreases. So ketchup is an example of that. If you've ever pounded the back of a glass ketchup bottle, what you're doing is you're applying a shear force to the liquid, and temporarily the fluid becomes less viscous because of the force that was applied. That's a shear thinning fluid. A shear thickening fluid, which is what we just looked at with those previous 2 YouTube videos, is where the fluid becomes more viscous as a shear force is applied. So this graphical illustration is that a Newtonian fluid is not affected. Its viscosity doesn't change depending on what force is applied. But a shear thinning fluid becomes less viscous as the force is applied, whereas a shear thickening fluid becomes more viscous. So I'll give you a cornstarch and water mixture in lab next week and a spoon. And if you stir the spoon slowly, then it's easy to stir. But if you try to suddenly move the spoon really quickly through that cup of the liquid, then the liquid resists the movement. So it's kind of an interesting experience that we'll look at in the lab next week. We are out of time. We're going to have to talk about the gas laws in class on Tuesday. So let me just spring back over here to the announcements before we go. Remember that what you need to be focusing on is get the book, do the Teams call, during my office hours preferably, but other times are also okay. And then homework 1 is posted now if you want to get an early start on that. All right. So that's it for today. I will see you on Blackboard Collaborate Tuesday, and I hope you have a good one. Bye-bye.
Thank you.